Hello, myself Dr. Pinaki Pratim Acharya, Professor, Department of Computer Science and Engineering, Huldesh of Technology. Today I will discuss on the deadlocks in operating system. I'll start with the definition of deadlock. So a deadlock in an operating system is a situation where two or more processes are unable to process because they are each waiting for the other to release a resource. So what does it mean basically? This particular definition says? In our operating system, in our computer system, basically we have infinite number of processes and finite number of resources. So the resources may be hardware resources or software resources, but we know the resources in our operating system, in our computer systems are finite and the number of processes are infinite, right? So what happens basically whenever the processes are in execution at that time, the infinite number of processes competes for the finite number of resources to complete their execution, right? So whenever this phenomenon is going on at that time, it might be the case that some processes may be in the waiting state for their input output devices to complete their execution, and this particular input output devices are busy with some other processes in their execution. So what happens? For some processes, their waiting state never ends, right? So this situation in our operating system is called the deadlocks. As some processes may not be executed, they may reside in the waiting state for their entire lifetime. So at that time, we can say the system is in unsafe state, and the system is in unsafe state means the system is in deadlock situation, right? So after that, in the system model, we need to know that the system consists of resources, as I have discussed, and processes. So the system consists of resources. The resource types may be R1, R2 to Rm. Suppose one resource R1 is the printer, R2 is the monitor, and like that the Rm may be the scanner. So these CPU cycles, memory space, input devices are very much important in this factor. Now for each and every resources Ri, it may be that it have Wi instances. It means for R1 process, it may be that Wi number of instances may be there. Suppose in a computer system we have one particular resource. The resource may be a monitor. Now the instances are, suppose W1 and W2. It will denote that two instances of R1 is there. It means two monitor is there. Same like suppose the resource Ri is a printer. At that time, suppose the W1 and W should be the two instances of that particular printer. It means with a particular system, two printers are attached. So here instances means number of that particular resource. Okay. So each processes what happens utilizes a resource like to give request to use that particular resource. Then the resource is being used, and whenever the execution is done with a particular resource, it will be released. So request, use and release, these three things are there with the resources whenever a process is in execution with those particular resources in the system, right? So instances are number of that particular resource. Okay. Now whenever the deadlock arises in our system, at that time 4 conditions need to be held simultaneously. These 4 conditions are mutual exclusion, hold and wait, no preemption and circular wait. So first, the mutual exclusion. Only one process at a time can use a resource. So this is the condition. Only one process at a time can use a resource. Whenever one process will in execution with a particular resource, at that time no other resource will will give request to use that particular resource. Mutual exclusion. So all the processes would be in a mutual manner, that suppose if one particular process is using one particular resource, any other process will not request for the particular resource. This is the mutual exclusion condition. Second, we have the hold and wait. The hold and wait says a process holding at least one resource is waiting to acquire additional resources held by other processes. It means suppose one particular process is holding one resource and it wants another resource for its completion or some other additional resources held by the other processes. At that time, if one particular process is holding one resource, at that time it will not request for any other resource. It have to wait. So hold and wait. Third one, the no preemption. A resource can be released only voluntarily by the processes holding it after that process has completed its task. It means suppose it may be the case that one particular process is busy with a particular resource. At that time, whenever the execution will be done of that particular process with a particular resource, it have to release that particular resource. So it says that a resource can be released only voluntarily by the process holding it. Again, some other condition is that in this no preemption, that suppose one particular process is using this particular resource, using one particular resource. So at that time, that particular resource will be only voluntarily released by the particular process into some other processes, and the condition is whenever the other processes will complete their execution, that particular resource will be given back to that first process which released that particular resource, right? So this particular no preemption is there. And the circular wait. So there exists, suppose there exists a set of P0, P1 to Pn number of processes, of waiting processes. So here P0 is waiting for a resource that is in use by P1. P1 is waiting for a resource that is used by P2. So like this, Pn minus 1 is waiting for a particular resource that is held by Pn, and Pn is waiting for a resource that is held by P0. So like this, whenever a circular wait will be there, where one process want to execute another process and that process is busy with some other. So like this, whenever the circular wait will come, as at that time, we can say this is the circular wait condition. So to occur a deadlock situation in our operating system, whenever all these four conditions will hold simultaneously, at that time the deadlock may occur in our system. After that, resource allocation graph. So as we have discussed with the four conditions, the deadlock may occur whenever these four conditions will occur simultaneously. At that time, what happens? We can understand, we can describe the deadlock situation with a graph, and that particular graph is called the resource allocation graph. In a resource allocation graph, there are set of vertices and set of edges. So vertices are denoted by V and edges are denoted by E. So here V is partitioned into two types. First P and R. First is P and second and R. So P, what P says? P says P1, P2 to Pn, the set of consisting of all the processes in the system. So set of consisting all the processes in the system are denoted by P. And R, the set of consisting of all the resource types in the system. R1, R2, Rm. So this is denoted by R. So the V is partitioned into two types. The set of consisting of all the processes in the system, which is denoted by P, and the set of consisting of all the resources in the system, that is denoted by R. Again, two very much important thing, one is a request age, another is the assignment age. Requesting age like Pi to Rj. So directed age Pi to Rj. It means Pi is requesting for the Rj resource to use, and assignment age directed age Rj to Pi. It means Rj to Pi, it means that it's a assignment age, means Rj is busy with Pi, right? Requesting age Pi to Rj, Pi is requesting to acquire Rj. Assignment age Rj to Pi, where Rj is busy with the process I. Okay, so Again, the symbols there we need to know that in the resource allocation graph for the processes, this circle will be there. Resource type with 4 instances. Suppose 4 instances are there, so you can see that in this square we have 4 square boxes. It denotes that 4 instances of a particular resource is there. So the processes are denoted by the symbol square. The resources are denoted by the symbol processes are denoted by the symbol circle. The resources are denoted with the square symbol. 4 dots or 4 squares are there within a square. It means the 4 instances of a particular resource is there. After that, the third one, PI requests instance of Rj. So it's a requesting age PI to Rj. It means PY want to acquire one instance of Rj or all the instances of Rj. If this arrow is there with a particular instance, at that time one particular instance is asking by the PI, and this is, if this arrow is there with the entire square box, at that time PI is requesting for all the instances of that Rj resource, R resource. Fourth one, PI is holding an instance of Rj. Here it's a assignment age where we can see that one instance is there assigned with the PI. It means PI is using one instance of resource Rj, right? So these things we need to remember whenever the resource allocation graph we will discuss. Now, example of a resource allocation graph. Here you can see that 4 processes are there and 3 processes are there and 4 resources are there, right? Resource R1, R2, R3, R4, process P1, P2, P3. Here one instance of resource R1 is there as one dot is there in the R1 square. 2 instances of R2 is there as 2 dots are there in the R2 square. 1 instance of R3 is there as 1 dot is there in the R3 square. 4 instances of R4 is there, 3 instances of R4 is there in the R4 square, and in the circle P1, P2, P3 is there. So what is going on in this case? See, first P1 is busy with R1, P1 is requesting R1 resource, R1 is busy with P2, P2 is busy with P2 is asking for R3, R3 is busy with P3, R2 is one instance of R2 is busy with P2 and one instance of R2 is busy with P1. So here in this case we need to understand whether the deadlock will occur or not. Here we can say that the deadlock will occur or not occur, right? So we'll come to this condition whether deadlock will occur or not occur in this case. So let's move to the second resource allocation graph with a deadlock. Here the same resource allocation graph is there, but one instance of R2 is requesting by the P3. So if I move to the previous diagram, this diagram, here we can say that deadlock will not occur. Why deadlock will not occur? Because as this P2 is busy with R3 and this P2 is using R3 and R1 is busy with P2, again this particular R2 is busy with P2. So whenever this one resource will be with the P2 and the use of that particular resource will be over, at that time we can see that this particular resource allocation graph will denote that no deadlock will occur. But in this diagram what happens, one extra requesting edge from P3 to resource R2 is there. So in this case as 2 resources are there and one resource of R2 is busy with P1, one resource of R2 is busy with P2, and P3 additionally is asking this particular one resource or maybe another 2 resources of R2. So in these cases the deadlock will occur. Let's move to the another diagram. So in this diagram the one instance of R1 is busy with P2, one instance of R1 is busy with P3, one instance of R2 is busy with P1, another instance of R2 is busy with P4. So in this diagram, whether deadlock will occur or not. In this diagram, deadlock will not occur. So how we are basically identifying them? If we move to the first figure, we need to check whether any cycle exists or not. It may be that preliminary cycles are existing, but whenever the execution of the process will be done with a particular resource, the cycle breaks. At that time, the deadlock will not occur. And this cycle basically breaks in this particular diagram. In the second diagram, the cycle will exist as one extra edge from P3 is there to R2. So deadlock will occur. And in this third diagram, as it looks like one cycle exists, but basically whenever the P2 will release R1 or the P4 will release the R2 after their completion of their execution, at that time the cycle breaks. So in this case also we can say the deadlock will not occur. So whenever in a resource allocation graph a pure cycle will occur, at that time we can say deadlock will occur. And if no pure cycle will not occur, at that time the deadlock will not occur. We can easily say that one. So this is the case as we were discussing. If graph consists no cycle, no deadlock. If graph consists a cycle, at that time if only one instance per resource type, then deadlock will occur. If several instances per resource type, possibly the deadlock may not occur. Okay. So these are the discussions, these are the scenarios in the computer system whenever the deadlock occurs. So basically we say that if there is no deadlock situation in the system is in safe state, and whenever there will be deadlocks in the system, at that time the system is in unsafe state, right. So if we take a quick recapitulation of this particular class, here we can say that in our computer system finite number of resources, finite number of processes competes for infinite number of processes competes for finite number of resources. For this, some processes moves in a waiting state and sometimes their waiting state never ends. So this particular situation is called the deadlock situation. So when there are four conditions of the deadlock situations where deadlock may occur, here mutual exclusion, no preemption, hold and wait, and circular wait. So these conditions, whenever all these four conditions will hold at a time in the system, at that time deadlock may occur in the system. So whenever deadlock will occur, at that time system will be in a unsafe state, and whenever deadlock will not occur, system will be in a safe state. Now this particular deadlock situation can be described with the resource allocation graph, where in the resource allocation graph we have the processes and the resources, and if there is cycle exists, at that time one instance per resource type, then deadlock will occur. If several instances per resource type, deadlock will not occur. And if there is no cycle in the graph, resource allocation graph, at that time we can say that deadlock will not occur, right. So this much is there for today's discussion, and we will continue our discussion in the next class. I hope we will meet in the next class. Thank you.